Hi, my name is Min-Soo Roo and I'm an associate professor at KAIST. Today I'll be presenting some of our ongoing work on designing a near-memory processing architecture for training recommendation systems. Before we dive into our proposed architecture, let me first lay out some background information on what is the main scope of our study. It is no secret that deep neural networks are both compute and memory intensive. As such, we have seen a lot of processor architectures focusing on accelerating these dense, compute-intensive DNN layers, achieving high efficiency improvements. Unlike these prior work focusing on accelerating dense DNNs, our research focuses on personalized recommendation models, which employ these so-called embedding layers. Embedding layers are interesting because, first, they account for a non-negligible proportion in the end-to-end inference latency, and second, they are extremely sparse with high memory capacity and bandwidth demands, rendering its characteristics drastically different than prior dense and compute-intensive DNN algorithms. More concretely, embedding layers consist of two key primitives, embedding vector gathers followed by vector reductions. As the embedding gather operation is conducted over a large embedding table, typically sized at several tens to hundreds of gigabytes, both embedding gathers and reduction exhibit high memory intensity, the throughput of which is bottlenecked by the memory system's performance. So, to address the challenges of training these sparse embedding layers, we propose a near-memory processing solution for training DNN-based recommendations, an approach we have previously explored under the context of recommendation inference. The key to our approach is to augment the buffer device within a DIMM module with a lightweight near-memory processing core, specialized for conducting vector gathers and reductions. We call these tensor DIMMs, and because the near-memory processing unit are stationed locally within the DIMM module, the memory throughput intensive embedding layers can entirely be conducted locally within the DIMM device. Unlike conventional memory systems, whose effective throughput of embedding operations are bottlenecked by the interface between the processor and the DIMM modules, TensorDIMM can drastically improve both latency and throughput of embeddings as all the key primitives are conducted near memory. Utilizing these TensorDIMMs as basic building blocks, our final proposition is to aggregate multiples of TensorDIMMs as a pooled memory architecture, which allows the several hundreds of gigabytes of embedding tables to be stationed entirely within the pooled memory node. The pooled memory architecture, augmented with our near-memory processing units, is integrated inside a high-bandwidth system interconnection fabric, NVLink for instance, assuming a GPU-centric AI system. You can also imagine the pooled memory node being integrated inside the recently announced CXL fabric, assuming CPUs or accelerators for machine learning such as NPUs are being utilized for accelerating DNNs. Such system architecture design allows high bandwidth and low latency communication between the pooled memory and the machine learning accelerator, whether it be GPUs, CPUs, or NPUs, drastically improving the performance of recommendation inference. So in this research proposal, the question we wanted to answer was, could near-memory processing architectures be equally effective for training recommendation systems as well? Before we jump into our proposed system, let's quickly go over how existing solutions are designed. An interesting property of machine learning accelerators for training purposes is that they're almost always optimized for a single compute primitive, general purpose matrix multiplications, or GEM in short. The question is why? Well, it turns out that a good chunk of important DNN layers, such as convolutional layers, are utilized for computer vision algorithms, recurrent or fully connected layers used for natural language processing, and other key primitives utilized for reinforcement learning algorithm are all amenable to be accelerated using the GEM primitive. The reason why this is possible is because the key primitives of both forward and backward propagation of convolutional, recurrent, and fully connected layers can all be casted or permuted to GEM-style operations. So why is such feature important? Well, basically, having a single operator be the target of acceleration allows the underlying microarchitecture to be tuned and optimized for that one operation. In our case, the dense and compute-intensive GEM operation. So with such property in mind, let's take a look at how DNN-based recommendation models are structured and what are the procedures taken in order to train these embedding layers. As you can see here, recommendation systems can broadly be partitioned into two parts. the front end sparse embedding layers, and the back end dense CNN layers. Focusing on the front end embedding layers, let's take a look at what happens during the course of training these embedding tables. During forward propagation, we gather multiple embedding vectors from the embedding tables, the result of which goes through a reduction or concatenation, followed by a feature interaction stage, which is forwarded to the back-end DNN layers. During backpropagation, because the embedding vectors that have been gathered during forward propagation are part of the model parameters that are subject for training, what needs to happen is we need to update those embedding values using the gradients backpropagated from the back-end DNN layers, which by the way is also memory intensive and is amenable for near memory acceleration. Now, because the compute and memory access characteristics of forward and backward propagation of embedding layers are dissimilar, the question that needs to be answered is, should we have to go about designing two separate accelerated microarchitectures, each optimized for forward and backward propagation respectively? While exploring such design space is certainly interesting, we take a different approach. We propose a decoupled, sparse-dense AI system for training recommendations. Inspired by Jim Smith's pioneering work on decoupled access execute architecture, we propose to decouple, partition, and specialize the AI training system into two parts. The part that handles the tensor load store operations from memory, and the other that handles compute over those fetched tensors. The key difference, however, lies in where those partitioning is being done, as our proposed decoupled sparse-dense AI system is constructed at the system architecture level, rather than at the processor microarchitecture level. Our decoupled sparse-dense AI system employs two types of accelerators, a sparse accelerator for training embeddings, and a dense accelerator for training DNNs, all of which are interconnected over a high-bandwidth CC-NUMA CXL fabric. When it comes to the dense DNN accelerator, the system architect can choose any commercially available machine learning accelerator optimized for training DNNs to flexibly compose the overall system architecture. For the sparse accelerator that handles embeddings, we employ a pooled memory buffer node design, similar to the previously discussed tensor-DIMM-based disaggregated memory system, all of which are augmented with near-memory processing units, specialized for training embedding layers. Now, as I mentioned in earlier parts of this presentation, it is important that the accelerator for training be optimized for the fewest possible number of compute primitives that can cover both forward and backward propagation. Our proposed near-memory processing core inside the sparse accelerator is designed to handle both forward and back propagation of embedding layers under a unified microarchitecture design, which eases its implementation and tuning for high efficiency. So with these sparse-dense accelerators in place, the runtime system software utilizes the sparse accelerators to execute the front end of training recommendations, properly fetching and storing back the tensor inputs and outputs, but doing so in a high throughput fashion as it is powered by our near-memory processing cores. Once the tensors are fetched by the sparse accelerator, they are transferred over to the dense accelerators over the high bandwidth CXL fabric, going through the necessary dense computations required for training DNNs. When evaluated on our prototype system, our decoupled sparse-dense system architecture achieves an end-to-end 2 to 21 times training throughput improvements for representative recommendation models. Okay, so that's the end of this presentation, and I hope I'll be able to share more details about our proposed AI system in the coming months. Thanks everyone for watching.